Hello everyone and welcome to the Buidl Radio podcast. Today with you is me, Polina, and Andrei Sobol, and our guest today is Ignacio Hagopian. Andrei, can you share a little bit of context of our talk?
Yeah, today we will talk about multi-party computation ceremony for KZG Commitment that we will use in Protodanksharding. So everyone knows that Ethereum will have Danksharding in the future, and they will implement Protodanksharding in the near future. And for these things, we need multi-party computation for the KZG commitment. And all of these complex things we will ask Ignacio. So, Ignacio, how are you?
Hey, thanks for having me. Everything going fine. It's a pretty hot day here, so dealing with that.
Yeah, so Ignacio, can you share us what is your expertise and what are the best questions to ask you today?
Right, so I will consider myself an engineer and a cryptography enthusiast. So I'm actually someone that knows some stuff about cryptography, but I wouldn't call me an expert on that. Actually, it's really hard to call you an expert on anything here because there's so many things to learn and to be an expert. But yeah, I would say that doing Web3 engineering, I've been working in this space for 4 years. But mostly in the engineering front, some protocol development. And now I'm trying to dive deeper into applied cryptography stuff.
Right. So except for deep cryptography, is there anything else that is definitely not your expertise and we shouldn't touch upon today?
Well, I wouldn't call me an expert on many things. Probably coffee would be a good topic not to touch on. I don't have like a good taste for coffee. I just drink coffee because it's useful. So I know there are a lot of coffee experts in this space, so I'm not one of them.
All right, nice. I'm also drinking tea today. Okay, so let's start with like general context and everything around the ceremony. And the first one is, what is Protodanksharding and why do we need it?
Protodanksharding is a milestone in the Ethereum roadmap, which is part of, let's say, a new vision for Ethereum, which is to be a network where rollups are at the center of this stage. So it's like a rollup centric roadmap. And when you think about how rollups work, there are a lot of things to understand, but one of them is that you need to solve the data availability problem. So to give some context, rollups usually, if you were to explain with a few words, they kind of batch transactions and do the AVM execution of chain and calculate the new state roots. And what they do with Ethereum, which is the layer 1, they have to provide the data of that batch of transactions, and they post the new state roots. So under this new framework, the layer 1 isn't eagerly doing any kind of execution of those transactions. So the validity of the execution is solved in different ways. That kind of depends on which kind of rollup you are looking at. But apart from verifying execution, as I mentioned, the other big problem to solve is how to make the data available. And so why is that important? Like, why we need to solve this data availability problem? So probably one of the easiest rollups to think about and to understand all these are optimistic rollups. As a refresher, optimistic rollups basically just post the batch of transactions and the new state root, and there's an expectation that somebody else is taking the same batch of transactions that are posted on chain and replay the execution locally. And they should check that the new state root is the same that the rollup has claimed. And that's how the network keeps the rollup in check if it's behaving correctly or is something hairy going on. Now, if you think about this, some critical aspect is that the batch of transaction is available for others to replay the execution. If that isn't available, nobody can double check the rollup. And that's a big problem because if that isn't the case, you are just like trusting an external party and like a state of the world out there, and we don't want that. So Protodanksharding is a middle ground between what exists today, which is rollups posting data as cold data, and the full vision, which is full danksharding, which is like pretty complex. So Protodanksharding is like a middle ground, which has most of the cryptography part of the data availability solution in Ethereum, but still like strip off other kind of really complex stuff. So yeah, like in summary, Protodanksharding is a milestone where we start to get an initial solution for scaling Ethereum on a rollup-centric vision.
In the Protodanksharing, we have KZG Commitment. It's the way how we commit the data to the like proto shards. Let's call it proto shards. And my question will be why we need especially KZG commitment for it. Why we cannot use any other commitment for making the like commitment to the data. We can imagine that it can be like Merkle tree or it can be Fry, not the KZG commitment. Why we especially use KZG commitment for it?
Okay, so maybe it's helpful to talk about what is KZG commitment outside the context of the Protodanksharding, so to have some mental model to think about this stuff. So KZG commitments is a type of polynomial commitment scheme, and that might sound a bit cryptic. So if you think about polynomial commitments, you have polynomials, which you might remember from high school, maybe. So polynomials are simply these things like 1 plus x plus 3x squared plus 4x cubed. So it's basically a function depending on some number x, and do you use some kind of linear combination of the powers of the number. Why polynomials are useful? So polynomials are a really good way to do some kind of compression of data, because polynomials have kind of encode patterns, but maybe we can get to that later. So polynomials are just like functions, as you learn in high school, and commitment. In cryptography, a commitment is a way to have like a fingerprint of something. So maybe the easiest way to think about commitments is to think about hash functions. So let's say you have a long sentence or a paragraph or some long text, and you calculate the hash of that, and you get a shorter block of bytes. And this is usually useful because it has usually two properties that you want. The first one is that if you change the original text by any means, like you change a single letter or something like that, the hash function of that new text will be different from the one that you calculated before. And this process is technically named binding. So the commitment should be binding, which means that after you share the commitment, you cannot really change the original value that you committed to, because that's kind of the reason that you are doing it. So that's kind of the binding property of commitments. There's also some other property called hiding that is maybe useful depending on the use case. And that's more related to the fact that even if so let's say that I'm committing to numbers between 1 and 1000. So I think of a random number and do the hash of that, and I share it with you. And if for whatever reason you happen to guess what number I committed to, if you come up with a pre-image of that hash that has the same hash value, you will know that that pre-image is the same that I selected as a random number. So if I select the number 5 and do the hash, and later for some reason you guessed the number 5 and you did the hash and you got the same, you know that I selected that number. And that can be a bit problematic depending on the use case. There are some commitment schemes in which even if you come up with the same hash, you cannot be sure that I selected that value. But we can leave that aside because the hiding thing is not really that important for this context. The most important thing is this kind of compression of committing to something and not being able to change that after the fact. So that's kind of a big idea of polynomial commitments. So you have a polynomial and you want to commit to it. And to do that, you have like multiple cryptographic schemes. So we have these KZG commitments, you have this fry, you have other options like pairs and hashes and product arguments. But before diving into details, I think it's also interesting to notice something else. And polynomial commitments try to achieve something more powerful than simply hashing something. And it's this possibility of generating a proof of an evaluation of that polynomial. So let's say that I have some polynomial, whatever, and I calculate the commitment and I share it with you. And later you're interested in the evaluation of that polynomial at some point x equals 10. So you say, okay, Ignacio, let me know the evaluation of your polynomial at point x equals 10. And I do the calculation because I have the polynomial, and I say, okay, the result is 20. And I tell you, okay, the result is 20. And you are a bit puzzled because the only thing that you have is this commitment, because you don't know the polynomial. And you have my claim that that the evaluation is 20. But you don't have like any upfront way to check that is true, right? So these polynomial commitment schemes allows me to generate also a proof that that claim is true. So you can have this original commitment that I committed to for my polynomial and take this proof and actually do some computation on your side to verify that 20 is actually the result of that evaluation. That's a really powerful thing because it's kind of a more constrained concept of snarks, maybe, because you are verifying some computation without having the original, like, full witness of the calculation. But yeah, that's kind of the way you have to think about polynomial commitments. You have a commitment, you know it is binding, so after somebody gave you the commitment, you cannot really change the polynomial. And you can ask for evaluations of that polynomial and get proofs and check that and be sure that's correct. So that's like a summary of polynomial commitments.
So for a double check, that you say that if you try to compare the possible way how we can commit something to the Protodanksharding, if we try to compare it to the just simple hashing, you try to say that additionally to just compression of data, we can have the additional property of like snark friendliness. Let's call it snark friendliness, that you can just prove something additionally, not just the value, but some manipulation over this value. Am I right?
Right. Yeah, that's right. And also it has some implications on like how big is the proof compared to simply building a Merkle tree. In Merkle trees, you can only prove like members of, like, parts of this data that you committed, but there's no like additional structure created underneath that is useful for this like other kind of powerful evaluation proofs or something like that. To give a bit more context of why we are talking about polynomial commitments instead of Merkle trees for Protodanksharding, in the Danksharding design, polynomials are actually useful for the full Danksharding scheme because in full Danksharding there's going to be something that is called data sampling. So maybe it's useful to explain a bit that. So in the full Danksharding scheme, users can submit this new kind of transaction, which is a block carrying transaction. So you can post some block to the chain. And the way this will work in the full Danksharding scheme is that whenever like a new block is created and people or validators are doing attestations to that block, there's no expectation that everybody's downloading all the data from those blocks. But still, like you have a scheme in which you have data that is committed to blocks, but you're not expecting everyone to download all the data. So you have to come up with some kind of idea or solution on how this can be secure. Because if you think about it, whenever you, let's say you have a file in your computer, and that file is 1,000 bytes. Usually, if you are missing just a single byte of those 1,000 bytes, you can consider your file to be corrupted. So you have actually like no margin to really lose data. So it sounds like if I'm like trying to only sample some parts of this data that is in blocks, how I can be sure that there's like no extra, like single byte that is held by some malicious party to really corrupt everything. And the way that this works is that Danksharding is planning to use something called erasure coding. And erasure coding is a way, it's a pretty oldish idea that is used a lot in backup systems and things like that. But the idea is that you have a chunk of data, let's say you have a file of 1 megabyte, and you can do some transformation, let's say for that to be now 2 megabytes. And the trick is that now you only need 1 megabyte from these 2 megabytes to really reconstruct the original file. And that's incredibly useful because now you only need to find a way to claim that at least half of the file is available somehow. With that, you can reconstruct the original value. So hopefully that makes some sense.
Let's get back to the KZG commitments now. So I know that KZG commitments require the trusted setup because right now is a process of the ceremony for the trusted setup. So why do KZG commitments need the trusted setup in the first place?
Right. So in the polynomial commitments schemes, you have KZG commitments and you have other options. And one of the properties that you need to think about when selecting some of these options is like what are the trade-offs. So when you think about polynomial commitments, you usually try to understand them in different buckets. One of the buckets can be how big is the commitment size, because if you are planning to post the commitment on chain, maybe having short commitments is important to you. So in that sense, KZG commitments are really great because the commitments are really short. There are other polynomial commitment schemes where the commitment is bigger. Another thing that you might think about when selecting a polynomial commitment is big are the proofs, these evaluations proofs that I mentioned before. So maybe you want that the proof is short or that maybe doesn't matter. Also, you might want to know how fast the verifier can verify the proof. And one other important consideration is if the polynomial commitment needs a trusted setup, or if this is also named if it is transparent or not transparent. So what does this mean? Every polynomial commitment that needs a trusted setup, the reason for that is because in the cryptographic scheme description, there's an assumption that somehow, by some kind of magic way, you got the encrypted powers of a number. KZG commitments don't really care how you got them, but you need some kind of an initial configuration to run the commitment scheme. KZG commitments doesn't really explain to you how to get these encrypted powers of a number. It just assumes that you have them. And if you have them, the scheme is secure and is sound and everything will work fine. So KZG commitments have really great characteristics on this commitment size and the verification overhead, and it really excels in mostly every front. But you have this annoying like trusted setup in which somehow you need this magic encrypted powers of a number. You have this kind of trade-offs. There are other polynomial commitment schemes which do not need this trusted setup, but they pay the cost in some other way, like with bigger proofs, or verifying the proof takes more computation, or generating the proof is harder. So in the case of KZG commitments, this trusted setup, as I mentioned before, is an assumption that you have. So in the KZG commitments, you have polynomials, and if you think of polynomials, you have polynomials of different degrees. So the degree of a polynomial is the maximum exponent of the x variable. So if you have 1 plus x squared, the degree of that polynomial is 2. And if you have plus x cubed, that would be 3, etc. So for KZG commitments to work, you need somehow you need a number. Let's call it a secret number, tau, which will be useful that name for later. So you need some number tau that nobody knows what that number is, but you need the kind of the encrypted version of tau with all the powers up to the degree of your polynomial. So let's say that your polynomial has degree 3. That means that you need the encrypted version of tau, tau squared, and tau to the cube power. So that's a bit weird, because how you can come up with encrypted powers of a number that nobody knows? That seems like a weird requirement. For that is that we are doing this Ethereum ceremony, which is simply a protocol that is called powers of tau. And it's like a procedure in which you can generate these encrypted powers of a number in a way that you can expect this secret number to not really be recoverable or anyone knowing that number. So another way to solve this problem is to simply say, we will trust Ignacio to think of a number, and he will generate the powers and he will encrypt that. And we will trust that he will delete that number from everywhere, and he's like a good person. But the problem here is that if that number, for whatever reason, is leaked, really bad things will happen, and you can do some you break the cryptography of the polynomial commitment. Yeah, so the idea of powers of tau is to have something better than simply trusting one person or a group of people doing the right thing. And the idea of Powers of Tau is that you can allow multiple people to participate into this process of generating what you need, in a way that if only one person from that group of people do the right thing, and we can explain what right thing is there, then you have the guarantee that this secret number isn't leaked or it cannot be recovered. So let's say that 1,000 people participate in the ceremony. You only need that one person does the correct thing in order for everything to be sound.
Yeah, so you was one of the developer who developed the Go client for this ceremony in Ethereum. So my question is, you mentioned 1,000 people who can participate to the ceremony, and I want to ask what's the limitation of the amount of people who can participate in the ceremony, how we can scale it, how many people can be the part of the ceremony? Do we have some like bottleneck for it?
Right, that's a really good question. First, I want to clarify that I did an independent client of the ceremony. So there's like an official client, which is this one that you might know from, it's like web-based. I think it's ceremony.ethereum.org. That client was created by the Ethereum Foundation. The code is open source, and yeah, you can also check that. The Ethereum Foundation also incentivizes people to create their own clients, and we can later talk about why that's useful. But yeah, I just wanted to say that like I'm like an independent person out there that created a client. It's like not really like an official one, despite that I've seen a lot of people using it, which was great. Regarding the like how to scale these kind of ceremonies and like how reasonable is to expect that many people to participate. So one of the fundamental, let's say, limitations of Powers of Tau is that it's a sequential process. So what that means is that, let's say you have 1,000 people that want to contribute. In this Ethereum setup, there's a single sequencer, which is coordinating who is participating and coordinating like the protocol execution. And the problem here is that since the Powers of Tau is sequential, the sequencer is only allowing a single person to contribute at the same time. And the contribution, so this Powers of Tau protocol that each participant has to run on their machines, is a somewhat complex calculations. So it involves like elliptic curve cryptography. So it is like quite heavy. The problem here is that you have to, like the sequencer has to go through each one of these 1,000 participants one by one, giving them each enough time to do the calculation, to send that to the sequencer. The sequencer will verify that contribution and then give turns to the next person. So as you might imagine, any kind of sequential process is a bit problematic if you have a lot of people waiting to contribute, and if every contribution takes, let's say, 10 or 15 seconds. If you have 1,000 people and each turn it takes 15 seconds, it is like a slow process, and it's UX-wise is pretty annoying too, because you have to wait maybe a lot of time to participate. So yeah, I think there are like some more advanced twists of the Powers of Tau protocol to allow like parallel execution of contributions, like or doing some kind of pipelining. But the Ethereum Foundation, I think that the logic was trying to come up with like a pretty simple Powers of Tau setup to make like other people write clients without like messing with more complicated things. So yeah, I would say that the sequential nature of Powers of Tau might be plus the heavy computation that each contribution has to do might be the most painful part of the story.
Okay, so right now, today is 11th February, and it's about 40,000 people who contributed to the ceremony. So I'm curious, the ceremony will finish, I guess, in about 30 days from now. How do you think, once it finishes, do they just like cut all the people who are in line waiting? Or do they just like continue everyone who contributed their randomness and append it to the whole powers of Tau? Or do you just like, okay, it's finished, everyone else is out?
Right, that's a really good question. Like, where is the finish line? I think that a good way to think about this is to come back to the roots of when these powers of Tau protocol is safe. So if we remember what we said before, the assumption of power of Tau to run correctly is at least one person from everyone has to do the right thing. And the right thing is basically that when you participate in the ceremony, you will generate a secret that is local to you, that you can generate whatever you want. And you do some computation and you give that to the sequencer. That's kind of how you contribute. But the important thing is that after you do the contribution, you have to destroy your secret. That's what you need to do, and that's what I call doing the right thing. Doing the right thing is generating your secret, doing the contribution, and destroying your secret. So if you think about it, like, now there are like 30,000 participants. And what this means is that we need only one person from these 30,000 to do the right thing. So it seems to be like a reasonable assumption that is already true. I think that also after this public phase of the ceremony finishes, there's like another phase, and I think that they call that special contributions, because there are people that are planning to contribute from more esoteric places. Like some days ago, I got to talk with somebody that was planning to use my client in a satellite to do a contribution there, which sounds pretty interesting. So I think that they're having like this extra time for these special contributions because maybe they have more constraints. Like you're gonna expect to have maybe great internet connection on a satellite, or the bandwidth requirements are different. After that point, I guess, we will think that we have enough contributions. I think that the main idea of the Ethereum Foundation is that everybody that feels, everybody should feel like part of doing this for Ethereum. This is important for the future of Ethereum. It's important for its future security. And I think that also, like, community-wise, it's really nice to give people time to participate. I think that we are already on a number that is more than needed for like making this safe.
Right. I know that they do give out grants for all the different randomness sources. I was really curious if they will like publish everyone who got the grant and what kind of thing they did regarding their randomness. I didn't find it just now, so I hope that they will publish it eventually. So a question is, like, in the client that you've implemented, where do you take the randomness from and entropy?
Right. Yeah, that's a really good question because it's really related to the security of like the protocol. So in the case of my client, I do I take some reasonable source of entropy, which is a cryptographic random number generator. So this is something that you can have on like most computers. It's something that you can get from the operating system. So it is basically a way of generating random numbers that are cryptographically secure. So my client takes as a basis that. It's like a way that your machine can get randomness from the context. But also I added an extra feature which I knew it was going to be useful for these like more esoteric sources of entropy projects that people are thinking. And if you want, you can provide some extra flags to provide an URL for the client to pull randomness from an external source. I was inspired by this by talking with Mario Havel, which is a person from the Ethereum Foundation, which was working on a really interesting way of generating entropy. He worked on a little gadget that you can use with your cat, and depending on how the cat moves, that kind of captures that randomness, if you say, and make that available for some client to pull somehow. And I said, okay, so if you are only generating the entropy, it's really hard to like pipe that into the web client, because the web client is simply not accepting like that kind of arbitrary sources of entropy. So that's why I said, okay, if I kind of make an extra feature in my client that allows the user to give some whatever URL that they want, the client also pulls randomness from there when making the contribution, and mixes up with this cryptographically secure random number generator, and with that it generates the secret, and with that does the contribution, and later deletes that secret from memory. So I would say that my sources of entropy on this client are the usual cryptographic random number generator, and optionally this kind of arbitrary URL where you can pull randomness. As an extra need, I also added a third potential source of entropy, which is pulling randomness from the DRAND network. So this there's like a blockchain out there which is named DRAND, which its main purpose is to generate entropy that is cryptographically secure, unbiased, and has all these really nice properties. Because having randomness in blockchains is really useful and important for the safety of many cryptographic schemes. So you will find this, how I can generate randomness safely everywhere if you study in this space. So this blockchain is, main purpose is to generate randomness. So I also provide an extra flag in the client that if you enable that, you will also query the latest randomness from this network, and also include in the bag of entropy of the client to generate your secret.
We know that it's not like the first MPC ceremony in the blockchain. We know that before the ceremony, we have the Zcash, few Zcash ceremony for generating trusted setup. We have Aztec ceremony for generating Plonk trusted setup. So my question is, can we reuse for this ceremony some data that we already generate for example, for the Plonk ceremony, which made by Aztec, because it's in some way it can be somehow composable, because the Plonk use also KZG Commitment, so maybe we can use the Aztec as starting point, and if we didn't use it as starting point for our ceremony, why we didn't?
That's an amazing question, and I think it's not really well explained out there. So I'm not like an expert in other trusted setups. I haven't really participated, but the reason, I think there are like two main reasons why reusing other results of other trusted setups can be problematic. The first one is pretty straight, which is the trusted setup has some assumptions regarding which elliptic curve is using for generating these encrypted powers of this number. So first of all, if you are planning to reuse the result from other trusted setup, your elliptic curves that you are going to be using in your system should be the same as the ones that were run in this other trusted setup. And in the case of Ethereum, is using the BLS 12381 curve. And that's not the same curve that was used for Zcash, I think, and Aztec. I think they are using BN 284, I think. So first of all, you need like the same elliptic curve. Another thing that you need is that each trusted setup needs to generate these powers of the number up to some point. In the case of Ethereum, it's generating the powers up to 2 to the 12th power. Actually, the Ethereum ceremony is not only one ceremony. It's actually 4 ceremonies bundled together. So actually, when you are participating generating 4 different tau values, each of them to different powers. So the powers are 2 to the 12th, 2 to the 13, 14, and 15. We can talk about why that's needed. That's a pretty small setup compared to others. 2 to the 12th, yeah, it's like a big number, but like in relative terms, it's pretty small compared to others. And the reason for that is that these other trusted setups, such as Zcash and Aztec, they are generating this setup because they need it for snarks. Snarks under the hood use polynomial commitments, so that's kind of the relationship. At least like the modern ones, like Plonk uses polynomial commitments. For older ones like Growth System, the trusted setup is a bit different. But usually the powers that you need for snarks are much more. Like you need like to the power of 10 or 100 million, which is way bigger than 2 to the 12th, which is 4,000. So the problem is that, like, let's say that you are building some application that needs some snark, and then you need a trusted setup because you have a non-transparent snark. You cannot really use the result of the Ethereum ceremony because you don't have enough powers for your use case. So apart from these like details about which elliptic curve you are using, if that's the same as the trusted setup, or if you have enough powers, I think there's like another dimension that you have to think about, and it's the trust assumption. So if we are in the Ethereum ceremony, so we before starting to run the ceremony, we think, okay, do we want to start from scratch, or maybe we can leverage these other results that were generated before? Accepting some other trusted setup result is basically accepting that protocol was run correctly. And you have to think about if that makes sense to you, because you are kind of linking your security assumption of your network with other network security assumption. That's not usually a problem if you're planning to add more contributions to that initial setup. But you have to think about like if that's worth it, because it can complicate things, and if you end up having 30,000 contributions anyway, there's not like a big gain from reusing some other like trusted setup result. So in summary, you have like other trusted setups, and what changed from setup to setup is which elliptic curve you are using, how many powers of tau you are calculating, and this like one person out of n being honest assumption. So depending on that, maybe you can leverage others or not.
Related to the elliptic curve that Ethereum want to use, why Ethereum want to use BLS curve? Why not something like from MNT4, MNT6 family, where you can simply use this commitment in recursive snarks, in recursive Plonk? Why not MNT4, MNT6 family? Do you know?
Yeah, I think that's because all this Protodanksharding and Danksharding is happening at the consensus layer of Ethereum. So the consensus layer client already were dealing with this BLS curve for signatures, and they are doing like aggregation of signatures for when the merge happened. So it is really useful to keep using the same curve to avoid like adding more curves to clients that the clients are already using. So I think from that perspective is useful. I'm not really sure if they have considered other curves, but I think that leaning into simplicity might be probably the best argument. The only thing that you need for KZG commitments regarding the curve is that it's a pairing-friendly curve, because KZG commitments relies on pairings. So pairings is like an extra operation that you can do in some curves that is really useful to check some things. But yeah, I mean, the only requirement of KZG commitment is that you have an elliptic curve and it's pairing-friendly, so you can use whatever you want. So in the case of Ethereum, I think it's just like leaning on in a curve that was already used by the consensus clients, and yeah, that would make everything simpler.
Getting back to the tau numbers, what are the sizes of blobs of data that you can now put into Ethereum, and how long will they be stored after the hard fork happens, like once they are added to the Ethereum?
So the idea is that when you post some data to like there will be like a new transaction type where you can post data. It's like a blob transaction type, and you might think about, okay, so I have some chunk of data and how this kind of somehow transform into a polynomial. That doesn't sound like clear how that happens. The way that works is that you have like your blob of bytes, and you have to interpret those bytes as numbers. So these numbers are field elements of that elliptic curve that we talked before. So you're basically interpreting the blob of bytes as chunks of bytes which you can interpret as numbers. And these numbers you can think of them as coefficients of a polynomial. So basically you have, let's say, the first 32 bytes, that's a number. You can see that as a number, and that's the first coefficient of your polynomial. The second 32 bytes is the second coefficient, and you can go on with that. And that's kind of your polynomial. And that's how you wire a blob of data with a polynomial and do the rest of the KZG commitment. I actually lied a bit here because you have like two ways of constructing this polynomial. You can think of, I will generate the coefficients of the polynomial and build the polynomial that way. But in practice, what Ethereum does in Protodanksharding and Danksharding is constructing this polynomial in evaluation form. And what that means is simply defining the polynomial as if the polynomial is f, you define f of 0 equals that first number, and f1 equals to that number. So instead of being the coefficients, those numbers are the evaluation of the polynomial at point 0, 1, 2, 3, 4, 5, etc. That is done for performance reasons. It's really useful to have polynomials in evaluation form to do some KZG things. But coming back to your question, so you have the blob of data, you do this interpretation as a polynomial, and you do the KZG commitment part. So regarding sizes, these powers of tau, I mentioned before that were calculated up to 2 to the 12th power. And what that means is that you can have up to 2 to the 12th chunks of your data, and each chunk has a defined size, which is the field element size, which I think is 32 in BLS. So you have 32 times 2 to the 12th, and that's around 128 kilobytes. I think that's the first target of each blob of data, and I think each block can have up to, like, there's like a target of 8 blobs. So I think that you can post, like the expected blob size for blob data is around 1 megabyte. That's kind of the Protodanksharding target. The full Danksharding is trying to push that to be even more. But the problem there is that in Protodanksharding, you are not doing this data sampling that I mentioned before. So you cannot really keep, like, all this data is still in the block, and everyone is downloading all the data. So you cannot like keep pushing more and more blob transactions, because that will make really big blocks. And we know that really big blocks are like a big problem for bandwidth in the network. So it's kind of a middle ground. Like you have some blobs up to 8. I think the target is 8 and can go up to 12. But yeah, it will be like in total you can post around 1 megabyte of data.
And do you know how long do Ethereum plan to store it? Or are there any EIPs about that?
I'm not sure that's decided, but I might not be up to date with the spec. I think it was like something like a year. So what this means is that validators after a year or whatever period of time, they are allowed to delete these blobs from these previous blocks. And that's really like a really interesting thing, because up to now, every data in blocks we're expecting people to store that forever in a way, at least in archive nodes. That's actually one of the biggest problems of Ethereum now. Like if you want to run a validator, you need a lot of space. The last time I ran a full node, which isn't like an archive node, so I don't have like all the history. You needed like 300 gigabytes of storage, which is pretty annoying. So the idea with this is that since we will be adding even more data than today, we are like adding more to this problem. So the idea is that after some time, like validators are allowed to delete that data, and that's something that is expected. It's not that something that we are doing to make people more happy. The problem that we are trying to solve, coming to the roots, is the data availability problem. So we want a way to people to post data on chain and know that that data will be available in a defined period of time. That's kind of the problem that we are solving. We are not solving posting data forever. That's not the promise, and that's not needed for solving this rollup-centric roadmap. So I think it's a year, but I might be wrong and can be less or more. So
yeah, for some reason, at first when I read the spec, I thought that it will also be stored forever. It's just like not all the nodes will store it. So I was like, okay, that's going to be interesting. All right. So another question that I have, I really don't know what's the answer to it. So maybe you know, as we introduce the additional type of transactions to post the data blobs, do you know if there are any implications on the MEV, which is miner extracted value, with regards to new transaction type?
I don't know. I'm not a MEV expert, but I wouldn't expect that to be much relevant, because I think that MEV is really like immediate kind of call to action thing about producing the next block. So probably like they will be interested in that for maybe some MEV in rollups, but I don't know, maybe not, if like the rollup is already providing that data somewhere else. So I don't think that maybe has much to do with MEV, but I can be wrong.
All right. Okay, so it's about 30 days left of the ceremony, to be a part of the ceremony. Can you recommend the ways to participate, and what is the best way to participate? Is the browser extension enough, or should we download the clients? And what are your takes on it?
Or should we use your client?
Yeah, it's a time to advertise.
Yeah, so the first thing is try not trust anybody as like a good mantra. Maybe this is like a good opportunity to explain why there are many clients and what can go wrong and like how you can help to solve that problem. So let's say that the only client is the official one, this web-based one that you can go to ceremony.ethereum.org, and everybody contributes to the ceremony using that. Okay, so what can go wrong? So even if you have 30,000 people participating that way, let's say that like this web-based client was built by 2 or 3 or 4 people, I guess in the Ethereum Foundation and some external collaborators. And let's be honest, like nobody will, like most people of these 30,000 won't be reading the code or be double checking the implementation of the client. So let's say that one of those developers introduced some kind of backdoor in the code and is not really destroying the secrets. It's like sending the secrets somewhere else. So now we have a big problem, because even if like 30,000 people are contributing, in theory generating the secret and in theory deleting the secret, this secret is getting leaked. And if like this developer has these 30,000 secrets from everyone, it can reconstruct this tau number that we wanted not to be leaked. That's why, apart from having a lot of contributors, it is really important that you try to use as many clients that you can, because that mitigates some risks like this one of maybe some Ethereum developer that made this official client introduce something or made a mistake. It just shouldn't be like intentional. Maybe there's a bug in the underlying cryptographic library. So many things can go wrong. So if you try to use other clients, you know, okay, there was like this other group of people that did their own implementation. It's really hard to really think of multiple teams colluding into making every client send your secret somewhere else. So, and also like different clients are using different cryptographic libraries. So even if a cryptographic library has a bug, we know that other clients are using something else. There can also be a problem if you get esoteric in your browser. So what if your browser has a bug and could be hacked, or there's an extension in your browser that has access to the memory and can stole the secret? Well, now like everyone that is using the web-based client might be compromised. So that's why you can use this other client. For example, my client is a CLI client. It's not web-based. So you run it in your terminal. So yeah, the idea here is that I would encourage people to use as many different clients as possible. I mean, first contribute to the ceremony. I think that's like the first thing, whatever client you want. But if you want to spend maybe an extra minute, just try to use some other client. Can be my client, or I think there are some others out there, and that you will be helping to make everything more safe, because it's not about only how many people participate, but it's like the diversity of each contribution. So if you are doing your contribution from a really weird and not really used that client, you are probably contributing even more to the security than just using the most used client. But anyway, I mean, the web-based client, I think is really nice. It's super friendly, and it was built by the Ethereum Foundation, which obviously has a lot of stake in like the security of the network, and there's like no good reason for them to do some hairy thing. So the main risk might be something like a bug or something like that. But yeah, the good part is that you only need one person from these 30,000 or 40,000 to do like the correct thing, whatever the client that they use. And that can be you, so you have to trust anybody. So if you do that yourself, you will know that at least you are that person. And the rest, it doesn't matter.
what can be wrong if trusted setup will be compromised? What the worst case scenario will be in this case? If some attacker can generate, like, let's call it fake proof or proof using this TAO, this secret data TAO, what this attacker can fake?
Right. So if this TAO number is leaked, as you said, what this person can do is forge proofs. So what that means is that he can do this hairy stuff about, if I'm asking this person for the evaluation of the polynomial at some point, whatever, he can cheat and generate a proof that I will verify and that will be correct. So the implications of that is that it would break the Danksharding design. So what will happen is that somebody can include a blob of data in a block, and with this full Danksharding setup in which people are doing sampling of this data, and can convince everyone that apparently all the data is available, but actually I will destroy that data. So this result, an assumption that the data is available, is now false. Okay, so what is like a practical thing that can happen if, in that scenario? So, okay, let's say that there is a rollup that is executing batch of transactions and is posting a new state root of the rollup with, in theory, the blob containing the batch of transactions. So the assumption here, if we remember, is that this batch of transaction was available for everyone to take and re-execute to double check that the new state root was correct. But now we have this problem about we cannot really assume that anymore. So that the data can be retrieved, and that means that nobody can re-execute. Nobody can do this state transition and check for the new state root. And now that means that nobody can claim that the rollup was honest or not. And that basically means that the rollup security is broken, because if nobody can check that the optimistic rollup was executed correctly, then I'm just trusting the rollup that is doing the right thing. In the case of CKey EVMs, that's a bit more subtle. So in zero knowledge EVMs, what these rollups are doing is that they are posting the data. I can explain a bit more, some twists there. But they are posting, let's say, the batch of transactions, the new state root, and a proof that all the computation in the EVM for this batch of transactions was done correctly. Maybe you might think, okay, maybe this data availability problem wasn't that bad, because the only thing that happens is that the layer 1 verifies this proof, and with this proof we know that the rollup has calculated everything correctly, so it hasn't created Ethereum from thin air, let's say. So that's fine, but the problem with CKey EVMs is that you need the data anyway to reconstruct the state of the rollup. So let's say that a CKey EVM is only posting the state root and the proof of the computation, and it's not sharing the transactions or anything else. The only thing that you can know is that the rollup is executing things correctly, so it's not really doing hairy stuff. But if you actually want to know, okay, so what is my balance in the rollup, or do I still have this NFT in my wallet, or something about the state, you can't, because the only thing that you know is that the state of the rollup changed like in an unexpected way, but you don't know really what that state is. It's like similar to only having the root of the state, but not having the state. You don't know anything about like your balance or whatever without further proofs. So even in the zero knowledge EVMs, the data availability is important because that gives you a way to know about the state of the rollup, and that is useful to simply know about things about the rollup, or if you have to do some kind of forking of the rollup because something really bad happened and someone else wants to fork it or move along, you need the state to do that. So in summary, you can fake, you can cheat in the network, claiming that some data is available when it isn't, and that has some really deep implications for rollups in general. Maybe somebody else, if it is using these block transactions for some arbitrary data, maybe some NFT image, who knows? Maybe in that case it isn't a big deal, but in the worst case scenario, it will be pretty bad.
The attacker can steal money from the optimistic rollup and froze money in ZK-based rollup. Am I right?
Yeah, that's a good summary, yeah.
This is one of the reasons why I fan of the ZK rollup and work in ZK Sync, not in Arbitrum. Okay, so the last question will be, do you have a prediction how many people will participate to this procedure, to the multi-party computation? How many unique contributors we will have in the end? And maybe if you will have like very big mistakes, we will have a funny tweet that your prediction is totally wrong, but if you will guess number like exact the same amount of participants, it will be funny.
Wow, that's really complicated. Okay, so you use a very special word there, which is unique contributors, and that's a bit of hand wavy actually, because anyone can contribute from multiple Ethereum addresses or your GitHub account. So there's like some Sybil resistant measurements about you cannot really generate an Ethereum address today and use that to contribute. You needed some activity some time ago or something like that, so it's like pretty reasonable. But if you have multiple addresses, you can do like 3 or 4 contributions with each one. So unique contributions is a bit hand wavy, but yeah. Regarding the total, well, I don't know. I would say I would really like to cross the 50,000 mark. I think that would be amazing. But I will be a bit more conservative, and I will say 42,000.
I think if I'm parsing this right, if you go to ceremony.ethereum.org, they have latest contributions, which has like number, participant ID, and signatures. They have 40,000 already.
Oh, yeah?
Yeah. I mean, 50K is close to the moon.
Oh my God. Okay. Maybe I will change my number.
Right. Please do. I mean, you can approximate now.
Ask me again.
Right. How many contributions will we have in 30 days? How do you think?
I wasn't tracking until some seconds ago the amount of contributions, but I would say that 50,000 is a number. I would really like to cross that. I would say like 50,000.
Yeah, when I was submitting the contributions actually yesterday, I think I was in line along with 2,700 people. And there was like, I needed to get my laptop staying overnight so it got into the sequencer. I would assume the number may rise closer to the end of it as well. So let's see.
Yeah, there's a particular UX, I wouldn't call it like problem, but the thing that you describe is maybe annoying for people, because when you are waiting for doing your contribution, let's say that there are 1,000 people in the lobby, that's kind of the name that they use, like this space where everyone is waiting to do the contribution.
Yep.
So the way that the sequencer was designed is that each time it can select the next person to contribute, it will take someone at random. So it's not really respecting the order in which you join. So that basically means that if you join now, you have the same probability of being selected next as someone that maybe is waiting for the last 2 hours. So yeah, you can expect really long waiting times or maybe not. So yeah, keep your tab open and simply wait.
Yeah, or keep your CLI open and wait.
Oh yeah, that's true.
All right, I guess we're gonna wrap it up. Thank you so much for joining us today. It was really nice and comprehensible. Like, I didn't expect, to be honest. But it's really, if you want to know anything about the trusted setup for Ethereum and the ceremony itself, like, I think this podcast kind of nails all the points, actually. So yeah, thank you for that. This podcast was brought to you by 2 Ukrainians away from home. And if you ever would like to support our efforts, please instead do support Ukraine in the effort to fight Russia, that is a terrorist state, clearly. And you can do so in fiat or crypto using the website savelive.in.ua/n/donate-n/. And yeah, feel free to throw any crypto or fiat currencies, and we would absolutely appreciate it. Thank you so much for tuning in. Please subscribe in YouTube and Apple Podcasts, Spotify, and so on and so on. Thank you for tuning in. Please leave feedback and comments if you like this or not. We're actually working on making this podcast better, and we would appreciate any sort of feedback that you give us, because that will make us grow. Thank you so much. Bye.